Okay, so I hope you all had a good long weekend. Are there any questions about the class schedule and the lab sessions? So only 16 people turned up on Friday. Is that right, Colin? Okay. How many didn't come on Friday who intend to come this Friday? Okay. How many intend to come Monday, this coming Monday? Okay. So what we did on Friday is we talked about downloading the software. We can run it on the lab computers, but it's probably better for you to bring your own computers and laptops so that you can work directly onto those laptops during the session and you have everything saved there. Unless you're going to depend on the machines in the GIS complex, and then you're going to have to go back to work there during the week on your assignments. So if you can work on your own machines, that's going to be probably an easier way for you to go. If we double-click and we open Nova, let me just size this, okay, and we go to the list, to download the software. So who hasn't downloaded software on their machine and still intends to do so? Okay, so you go to the website here, and you can choose either the Mac or the Windows release. If you go, and here's the instructions on how to do this, you have to get the license, so you have to go to the license page. Not sure why that's not showing up. And if you go here, you'll see that there are new versions that come out. If you want to get the latest version, you can just download the latest version, but basically this version should be running all the software that we do in this class, and if it doesn't, I'll let you know. Are there any questions about Nova? Okay, and remember at the Nova website, if you want to review the interface, you can go to tutorials, and you can start the Modeling 101, this one, getting to know the Nova interface. And then in order to do your assignments, it's useful to go through 2A and 2B and 2C. It's up to you. It's certainly not necessary to do these. And those of you who came to the Friday session know that I went through on Friday on building some simple models, and I'm going to go through building a model today in class. I'm not going to continue to do this. So after a couple of weeks, when I put up a model, I'm not going to build a Nova version in class. And if I want to use it, I'll have a version that's already built. Because it takes a little bit of time, and it's just to get you familiar with the Nova platform that I'm doing this in the beginning. But the resources are there for you to learn Nova. And then your first homework assignment is due today, 2 weeks. So those of you who are coming to the Friday class, some of you will have had an opportunity to go through 2 labs. The Monday class will have this Monday and next Monday. But don't leave it until next Monday to get started with your homework. Okay, any questions about that aspect of the class? So you all know how to get to this website. Okay, so today we're going to talk about difference equations in a little more detail. And I know that some students prefer it when I talk on the board, and I also prefer to talk on the board somewhat, and so I'll come back to this. But in the meantime, let's go to talking about these kinds of models on the board. And I'm going to talk about this class of models, difference equation models. There are going to be a number of examples that I refer to here, example 1, 2, 4, and 6, and I expect you to go through these yourself, and I'll cover some of the ideas in some of these examples, and then I'm going to construct this model over here, which is part of your homework, and we're also going to talk about cobwebbing. But before we do that, let's just talk a little bit about models on the board. Okay. So in general, mathematical models are incredible simplifications of what's going on. And mathematical models are models that we can use to get quantitative information on what's happening to things of interest. So some of the first mathematical models in the early 17th and 18th century had to do with how the planets and solar objects moved in space. And then, of course, once Newton's laws of motion were formulated, we got interested in models about how trajectories move through space. Why would we be interested in how trajectories move through space? Or objects move through space along a trajectory, yeah? Okay. So astronomy is a great one, and I don't know how many of you have camped out in the middle of nowhere where there are no lights, and all of a sudden you realized why 2,000 years ago people were interested in the stars. Like you go out in the city and you look up and you say, I don't understand I don't get it. But if you go out on a moonless night in the middle of nowhere, then you get it. And especially when you see things happening, especially when you see the sun rising and the moon setting, you're going to make up all sorts of stuff about how the world works. And so Newton was very smart. Why is it still showing when I close my... That's weird. Magic. Huh. Okay, forget it. But there's another reason why we're interested in how things move through space. What are some other reasons? Yeah? Okay, so there's a notion of time. How many of you know Zeno's paradox? Anybody know Zeno's paradox? So Zeno posed the following paradox. This is a race between Achilles and a tortoise, or Achilles and a hare. I can't remember which one. Anyway, there's lots of different versions. So here's Achilles, and the hare starts, let's say, over here. And Achilles starts over here, and he's going to race the hare to see who hits the wall there first. So the race starts, and Achilles runs. By the time he gets to where the hare was, the hare has moved on. And then he goes again. By the time he gets to where the hare was, the hare has moved on. And so there's these intervals of time that he keeps closing the gap, but there are infinitely many of them. So how does he ever overtake the hare? How? Yeah? It's the illusion of motion. Okay, I mean, that is an important one. What is motion and how is it an illusion? But there's kind of a deeper mathematical issue here. Huh? Yeah, so if he runs faster, then it takes him a shorter time to keep catching up to where the hare is, but he never gets, because the hare's always an infinitesimal distance ahead of him, and he's closing in. Yeah? Yeah. Right, so technically becomes 0 is kind of a sleight of hand that we actually use in a sense. So if you take 1 plus a half plus a quarter, so you can work this out, plus an eighth plus a 16th, and you have infinitely many of these. Sigma I equals, let's see, from 0 to infinity, we write it that way, symbol of infinity, 1 over 2 to the I. So we start out with I equal to 0, which is 1, I equal to 1, which is a half, I equal to 2 is a quarter. So this sum actually equals what? 2. Okay, how do we know this? So we don't really know this. We accept it. This is the miracle of calculus. So when Newton invented calculus and Leibniz invented calculus, they said if you accept this kind of fact, that sums of infinite things that get smaller and smaller make up something finite, then we can move on. And if we move on and we use these calculations actually tell us what happens and it works. So if you look at physics and physical theories and even quantum mechanics, there's some very strange things that these mathematical formulas say. And we wonder, how could it possibly work? And then we use those devices, like we say, a sum of an infinite number of terms can converge to a finite number. And when we do this, it works. And we get answers. And those answers, when we measure things, work. So in physics, in modeling, we do this sort of thing. And the test is how well it works. Now in physics, we can measure things very precisely. So we can predict how solar bodies move. We can predict when the next eclipse is going to be, and it works, so we accept the mathematics. In biology, it's much more difficult because things are not as precise. So we build lots of models, and people question them, especially like about global warming, global change. We make models. People contest them. Or we make predictions in economics. We have economic models. And then we test them, and they only roughly tell us what might happen, and sometimes they do very badly. When they do very badly, it's not about the mathematics, it's about the model. And so this is the problem with models. But another area of mathematics, another area of the application of wanting to see how things move in space, of course, are projectiles. We're interested in what angle we should shoot something so that it hits something. Why would we want to do that? Why would we want to calculate where a projectile is going to land? You can say it, because we're killers. If you don't believe it, watch the news. But anyway, civilization and socialization is about taking the killer out of each of us. So who feels like a killer today? Come on, I bet you wouldn't think twice about killing a fly or killing an ant, would you? So where do you stop? That's the question. We all kill insects very easily, which is, we'll get onto that a little later this morning. Okay, so we make these models, and models are highly simplistic. And if we're talking about a population, the simplest model we can have is how a population changes over time in numbers. And so we can call the total size of the population X, or we can call it N, or we can call it something else. And if we want to know what the population is at time t, we can either say what is X at time t, or sometimes we use a subscript. We tend to use a function of X of t when we think of X changing continuously over time. We tend to think of X as a subscript of time when we think of discrete points, X1, X2, X3, X4. But these notations are interchangeable, and you'll see them in different places. So now we say, okay, let's talk about what our models look like. So if I want to make a model of how the population changes with time, one of the things I can do is I can say, okay, I have this model X, and the value of X at t plus 1 depends on its value at time t. So that's called a simple scalar model. It just depends on a variable. And a possible version for this is it's just proportional to X. So this is a simple model proportionality. And so this says that for every individual I have at time t, I have r times as many at time t plus 1. Is that a reasonable model? So remember, we looked at the population of America, and we said that in 1815, each decade was growing 33%. So we made this number 1.33, and we kept growing the population. Did that work well? Well, it did seem to work well for 60 years, but then we saw that it was slowing down. So it was a little more complicated than that. But if we look at this as a model, x at t plus 1 is f of xt, then we can plot that on a graph. And if it's easier for you to think of this as y is some function of x, then when x is x at t, y is x at t plus 1. So I can plot this as a function yx. But instead of calling it yx, I'm going to call it x at t plus 1, and I'm going to call this x of t. So it's like plotting a function y equals f of x, and I'm plotting the function f. If I have a model like this, that's the same as saying y is equal to r times x. So what is the model y equals r times x? What would that look like in this space? What would it look like? What would the function f look like? A straight line through the origin, yeah. So this is just r times x, okay? Now I'm going to draw the 45-degree line. The 45-degree line is just f of x is equal to x. It's the same as saying if r is equal to 1, I get the 45-degree line. Everybody happy with that? Okay. So what usually happens, as x increases, do I expect this relationship to hold? On what basis would I assume that a relationship like this holds? If I said to you the population increases by 20% every unit of time, what assumptions am I making? Yeah. That there's unlimited resources, no external effects, kind of intrinsic to the population, its ability to increase when under, let's say, ideal conditions. The conditions are never ideal, and resources are limiting. So I can either take resources explicitly into account, and we'll talk about that later in the course. But if I take resources implicitly into account, then I say R itself is not going to be a constant, but it's going to depend on x. And in a sense, there's a notion of competition in there. So when there are only a few individuals, we all want to grow, and we need resources to grow, and we go around and get these resources. If we're not interfering with one another, we are at our kind of intrinsic maximum capacity to reproduce. But if we start interfering with one another, then what's going to happen, instead of this line continuing straight up, what's going to happen to this line? What do you think? It'll start to turn over. So, it may start to look like this. But then something like this happens. And finally, it may level off. If it levels off, what am I assuming? Yeah, okay. Okay. So if it's leveling off, then you have this idea that the environment in each generation can just produce so many new individuals, irrespective of the number of individuals over here. So then it begins to reflect, in some sense, something intrinsic about the environment. So, for example, a function that behaved like this, what would a function that behaved like this look like? Instead of just being r over x, it would be over 1 plus x, and I'm going to divide by k. So it starts out like r over x, but at some point, it begins to saturate. Now, how do I know that this function saturates? How could I test that this function approaches a constant? How could I do that? How could I do this? Yeah? Well, if you take r over this, and you leave out this x, so now we've replaced the r with something that is a function of x, and yeah, this goes to 0 as x gets bigger and bigger. So that's one way. Another is to say, what is the limit as x tends to infinity of rx over 1 plus x over k? Well, if I divide the top and bottom by x, that's r over 1 over x plus 1 over k. So this goes to r divided by 1 over k. So this goes to r times k. Now k has a special meaning, because if I put x equal to k, then I get 1 k over k, which is 1. 1 plus 1 is 2. So instead of having, this would have slope r upon 2. So in a sense, x equal to k is when the rate is reduced by half. So you can k sometimes called like the half saturation parameter. So that's why it's good to put x over k, because it helps you scale x. It tells you at what point and for what value of x you reduce by a half. So now we've got this equation. F of x is equal to r times x over 1 plus x to the k. Is it possible to get something that looks like this? That it would start to go down. Is it possible that as the density went up, things got so bad that the total capacity for the environment to produce new individuals goes down with increasing number of individuals? Can you think of a situation where that could arise? Yeah? Exactly. If they hurt the environment. That's a very kind way of saying it. If we really messed it up. I couldn't think of worse things to say. So this is called compensatory, and this is called overcompensation. And what happens is that you can mess up your environment. Now, for example, if you get if you get, for example, a moth, and the moth lays eggs on a tree, on a whatever kind of tree, a nut tree, whatever, and the larvae hatch and they eat the leaves. Now, you can imagine that at low densities, if each larva needs a few leaves, and there's just a few larvae on a tree, they don't interfere with one another. Then they begin to interfere with one another, so that some actually, just by chance, have lots of other individuals near them and don't get enough food and die, and others are fine because they don't have that many individuals near them. But imagine the whole tree was loaded with eggs, so that every leaf had several eggs on it. And all individuals started eating, and then by a certain point, they all run out of leaves, and nobody has got to the point where they're big enough to molt, or to spin a cocoon, or whatever. And so they all die. So in other words, you can mess up the system so badly that everybody can die. On the other hand, if there are lots of individuals, there may be a lot of conflict. And in that conflict, a lot of individuals kill each other until there are only a few left. And so there are various mechanisms by which this can happen. So how can we build a curve that looks like that? Or is it possible to build a curve that takes both of these cases into account, depending on the value of a parameter? So it turns out that if we write this as f of x equals r times x over 1 plus x to the power k, 1 plus x over k to the power gamma, then if gamma equals 1, we get this curve. But as gamma increases beyond 1, so this starts to turn down, and it becomes more and more peaked for a larger and larger value of gamma. So in your homework assignment, I've asked you to plot this curve for different values of gamma, so that you can see that, in fact, this is true. And again, you don't use NOVA to do this,